And you might wonder, who is Global MRV? Who are we? We provide portable emission measurement systems and data capture and analysis solutions. So we're trying to capture as much data as we can. We're trying to make it easiest for you to be able to do this, and most of the time in a real driving conditions. Like I said, we're based in Cheektowaga, New York, which is a suburb of Buffalo, New York. And if you like NFL football, you know the heartbreak that we just went through here. We've served businesses, original equipment manufacturers, research facilities in transportation, automotive, engineering sectors. Our PEMs, and of course, I'm going to say it, but it's absolutely true. Our PEMs are reliable, accurate, cost effective, and they give you on road data acquisition, the emissions testing analytics. So it makes it much easier to get that cutting edge technology into the vehicle out while it's moving around. And that includes, trains, trucks, ships. We've tested so many different things and participated with so many different manufacturers. And so that's what we do here at Global MRV. Specifically, my name's Earl Leatherland. I've worked at Global MRV for about 15 years now. Trained in Six Sigma practices while I was employed with General Electric. I've worked with engine emissions quantification, research and development, and just overall vehicle performance and health for the last 15 years. Well, I guess now it's 16 years now that I think about it. Time really flies. And once again, that includes all types of transportation, from handheld power equipment, which isn't really transportation, but internal combustion engines, to trains and trucks, research and development, all types of vehicles, anything mission assessments that are needed for any kind of companies. And we'll discuss some of that today. So as we're going through, what are we talking about today? It's got specifically to do with N2O, nitrous oxide. It's a potential greenhouse gas, or a potent greenhouse gas. It's one of the ones that really sticks out. If you were in the webinar last month, you heard us talk about all the different types of greenhouse gases, the most prominent ones, how they relate. We're going to go through a little bit of that just really quickly today, just to remind you if maybe you missed it. So global warming potential for this greenhouse gas for N2O specifically is about 240 to 273 times that of carbon dioxide. I look at different papers and they give about that range. It's got an atmospheric lifetime of about 114 years, which is why it makes it so important to try to mitigate it, because once it's in the atmosphere, it's going to stay there for quite a while. Now, just to go back through quickly, and we're just going to go through this stuff quickly. Here's the major greenhouse gases and the global warming potential of each one. Got water vapor, carbon dioxide, methane, nitrous oxide. That's the one we're looking at today, and the fluorinated gases. Now, with nitrous oxide, you'll see the study that I looked at it's got a global warming potential of 273 times that of carbon dioxide. So it's much larger. You can see it's much more larger than methane. Once again, carbon dioxide is the one that we base everything off of. It's our reference number, if you will. This gives the balance of, you can see, and actually it's actually hard to see, nitrous oxide. It's so small, it looks like, okay, why do we pay attention to it? For all the greenhouse gases, here are the ones, the sulfur hexafluoride, nitrogen trifluoride. These are things that have a even higher global warming potential. Let's take a look at those really quick. And also the greenhouse gas potentials percentages in the actual atmosphere. You see 4% for water vapor, carbon dioxide, methane. You see it shows nitrous oxide as such a small percentage. So why do we find it important? Once again, based on our discussion from the past few weeks, water vapor looks like it's the biggest one. But here's what we're really looking at. This is what I created this. It's a greenhouse gas visualization of influence. So water vapor, even though it's the most abundant in the atmosphere, it actually doesn't have a high global warming potential because it doesn't exist in the atmosphere very long. We're talking about a water molecule exists in the atmosphere for maybe 2 weeks, falls back into the whole, condensation, evaporation cycle. Carbon dioxide stays in the air not quite as long as nitrous oxide, but there's much more of it. So that's why it has a much greater influence, which is why we base everything off of it. It's the standard. It's a standard, if you will. Just want to make sure that everything's still working. I'm looking back at the loud and clear. Excellent. Glad to hear it. Loud and clear. Perfect. All right. So I'll go back to it. You'll see that the carbon dioxide, there's more of it in the atmosphere, but it doesn't last as long. Whereas nitrous oxide, there's less of it in the atmosphere, but it lasts much longer, and it's got a higher global warming potential. You see everything compared with methane, hydrofluorocarbons, nitrogen trifluoride, all the different ones that we have. Like I said, I'm just going to go through this really quick. You could see this whole thing on last month's webinar if you'd like to take a look at it. So we were talking about specifically about global warming potential and how nitrous oxide affects global warming, how nitrous oxide is, part of vehicles, automotive. But one thing I'd like to take a look at really quick. I actually enjoy this. I don't know if you guys have ever seen Top Gear or not, but with nitrous oxide, N2O, it is actually utilized in so many different ways. It actually can be a useful gas. It's produced and utilized to make cars go faster. It's utilized as laughing gas. You might know it as laughing, and you might think, oh, these are different gases. These are the exact same gases. They're just utilized in different ways. So let's take a look, if you will, participate with me. Hopefully this will come out and it'll work okay. So here's how nitrous oxide makes a difference in the ability to boost your ride. And as always, I've got to make sure that let me skip over that.
Jaguar XJS was battered by the might of the world supercars in a straight line fight on our test track. But we're not going to leave it at that and give up. We're going to go back for another go. But this time, the Jag has got a little trick up its trousers.
Oh, why that?
So the Top Gear Warhorse is going to take on the best the world has to offer. How, you might ask, are we going to do that? Well, we're going to cheat, obviously. And we're going to do it with the help of the wizards of NOS. NOS is nitrous oxide system. That's this stuff. And the guys who fitted are the wizards. Trevor, you put all this in our car. How much difference is this going to make?
Well, the system's got the ability to deliver up to 500 horsepower extra.
500 horsepower over and above. Just very, very simply, how does it work?
We feed oxygen in the form of nitrous oxide into the engine. We'll mix that with an extra supply of fuel. The combination of the two turns in the engine and produces more power.
What if you get it in the wrong percentage?
If we put too much fuel in, it'll just belch out black smoke out the exhaust and it'll reduce power. If we put too much nitrous in, it could melt something.
What, like the engine?
Like the engine, yeah.
So you're probably going to break our car. And there they are. £500,000 worth of supercars nearly against 250 quid worth of rusty jack, albeit with a few hundred quid worth of nitrous added on. I just hope it makes it to the start line. So for this run, the nitrous will give our old Jeep an extra 200 horsepower, making a total of 500. But will that be enough? And will it hold together? Oh yes, and straight away you can see the difference. It's blowing away the Venturi, the Corvette, the Honda, and even the Ferrari 360. But the big question is, can it hold off that mighty Porsche 911 Turbo? Well, right for the old Warhorse, yeah, it just goes to show 250 quid worth of Jag, about 500 quid worth of nitrous, and it'll do a standing quarter in 13 seconds. And that's faster, as we've just shown, than a Porsche 911 Turbo and a Ferrari 360.
I've just found that kind of interesting. What can be done? What can be done with this type? Oh, I don't want to start that again. What can be done? So one of the questions I actually have for you guys is: have you ever actually participated or utilized things like a nitrous oxide, or maybe use nitrous oxide because the other place you use it maybe is at the dentist's office? This is the exact same gas that we're talking about in both these situations. Now you might wonder, Earl, why are you going through all this stuff? It doesn't make any sense. I thought we were talking about how we reduce emissions. That's what you do. I just want to we want to give an overall on what N2O is and how it contributes. And I just thought it was fascinating that the same N2O we use to make a car go fast and beat a Ferrari is the same thing that we put on our kids' noses at the dentist so that they can be relaxed, so that they can get their teeth clean. And unfortunately, N2O is even used in things like whipped cream, where kids are using those. That's what the whippets are. That's what whippets are used at the local 7-Eleven. So it helps us understand where this gas is, how it's utilized, both in a good ways and poor ways, but how it's manufactured, how it exists in so many different ways. So main contributors to N2O when we're looking at emissions and how it's reflected in the world are agricultural, and that breaks into synthetic fertilizer and animal manure, industrial processes. This is the one that we'll be, looking at the most today, the actual industrial processes, which are fossil fuel combustion, whether that's in industrial or in vehicles, which once again, that's the thing that's most critical to the ones of us discussing it here. Biomass burning, waste management, sewage treatment, and natural resources for the soils and the oceans. Now, one of the things that I found very interesting, according to a 1990 EPA research document, well, it was actually, it's done around 2000. It was 1990 to 1998. It shows what the EPA has estimated N2O is actually coming from, where it's actually being produced from. And you see the largest one here comes with agricultural, and that's broken into synthetic fertilizers about 45%, and animal manure at about 22%. So you're looking at 67% right here just in natural production. Industrial processes, which is the ones that are we're most interested in, we'll talk about today, is it's 10%, 7 and 3. The 3% being industrial and internal combustion engines. Only 3% coming from that. Biomass burning, waste management, and natural resources. Now, here's the one that makes it difficult for us sometimes to be able to assess, because I looked specifically at the EPA research documentation, and we found, I got a question here. I just want to make sure that I'm following up with the questions. Okay, yep, I see it. All right. With the natural resources, this shows 5%, but in a similar research, but this was done in 2019, you'll see much different numbers. Agricultural becomes 22%, and you'll see that this huge pie right here, I clicked on it and I shouldn't have. This huge pie right here is actually soils and oceans. Soils and oceans get up to almost 70% of all the N2O. So these are the exact same measurements. So it's not like I'm comparing one to another, and they're not I'm not comparing apples to apples. I'm comparing apples to apples here. So you have to make sure you're looking at what research document. This one, as I said, comes from the EPA. You can see the reference that I use here in the document that I used to get that information. And here, this is a group called Frontiers, and they produce journals and scientific journals and scientific papers. They're about the third largest supplier of scientific papers in the world. So they give a much different number here. But once again, you can see the small part that we're looking at, fossil fuel combustion, is about 0.3 of this whole pie. It's not quite a percentage. It's a little bit different here, but it's still very small percentage, as you can see. So when we're looking through all this, the main contributors, I wanted to make sure that we break them down quickly. I'm going to go through them kind of fast so that you understand, and it'll be easy for you to understand, even though if you're not a chemistry person, like I'm not a chemistry person, but it'll be easy for you to understand, because you'll see the information kind of repeats itself for agricultural, biomass, natural resources, and even waste management. You'll see some of the information repeats itself. So one of the main contributors, agriculture, and we're looking at the synthetic fertilizers. So the use of nitrogen-based fertilizers in agriculture is one of the largest sources. Now I put the largest source because, once again, I initially read through the EPA documentation, then I saw the Frontiers documentation. So it's one of the largest, not really the largest, depending on which documents you're looking at. And it's one of the larger for a source of N2O emissions. And this all comes down to microbial processes that are happening down in the actual fertilizer. So nitrogen, we all probably know, or it might be a review of your chemistry class from high school and college, that nitrogen is one of the most abundant elements and is needed for plants to survive. So synthetic fertilizers applied to the soil that increase the nitrogen content. And we see, this is this thing we'll see repeated over and over again with a lot of these processes, nitrification and denitrification. We'll see that a lot. We will see that a whole lot. So here you can see nitrogen. Once again, this is the balance on the Earth's atmosphere. 78% nitrogen, 21% oxygen. This is what we think about the most. This is what we're breathing. Well, we're breathing nitrogen as well. It's coming through us. Carbon dioxide, argon, you see the other breakdowns of it. But nitrogen is a huge part of our lives, a huge part of what we have. So when we're going through these synthetic fertilizers and we look at nitrification and denitrification, there's a whole chemical process on how that's done. Ammonium from fertilizers is converted to nitrite, NO2, and nitrate, NO3. And during that process, we release N2O. Denitrification is a little bit different, and I'll go down through them. I just went through that information. Denitrification, the process where soil bacteria converts nitrate, NO3, into nitrogen gas under anaerobic, remember, chemistry class again, low oxygen, anaerobic conditions. So that during that process, it's produced as an intermediate product. So it's not something that they're actually trying to, it's just something that's off-gassing, it's participating or adding to the atmosphere. Now that's in, chemical processing, making fertilizer. As we go to agricultural, animal manure is another significant source of N2O production. That's actually producing it of itself. Once again, it's got a lot to do with nitrification and denitrification, the microbial processes. And when we break down livestock, you see 70% of that coming from manure from cattle. Kind of disgusting that we're talking about this. Why aren't we talking about cars? We're going to get to it. Why aren't we talking about vehicles and combustion industry? We're going to get to it. But I thought this was interesting. Now, that meant there's different manure management practices that they can take in order to reduce this stuff, anaerobic digestion, frequent manure removal. There's so many different ways. A lot of this is being impacted by the large industrial, more industrial farming and industrial cattle raising than what used to be. Used to be people had their cattle out in the pastures. Now, when they contain them into buildings, it promotes that microbial activity and promotes that place where there's low oxygen because everything's inside the building. It's covered, not a lot of sun. So you have more of it being produced now than in past. Once again, you won't see that in your regular farmers that, your smaller farmers. It's more of the industrial complex type of farmers. And it can make a difference, soil conditions, temperature, and moisture levels. This is another thing you'll see repeat itself over and over. So even when we go to biomass burning, here's another section. When we go to biomass burning, you'll see that you have the combustion of organic matter. I was curious, because this is something that's prevalent and we see it just recently with LA fires. What happened with the LA fires and how did that affect us? So during that particular fire, the estimates, haven't come out yet specifically, but, the temperatures, we're looking at, 900,000 degrees Fahrenheit in some places, depending on how hot it was burning, how intense, how things were close together, which makes a difference in N2O production, the actual temperature. But the estimated emissions right now, they did carbon equivalents. We talked about carbon equivalents last time in the webinar, is about 3.67 million tons of CO2 equivalent just in the first 15 days. So that's part of it. Another part of it is soil disturbance. It changes the way the soil is. Microbial activity builds up. Once again, we get the nitrification and denitrification. This is the same with crop burning, biomass burning and the residues there, the direct emissions. So a burning crop, it releases N2O directly into the atmosphere, and the nitrogen in the plant material is converted into N2O, during that combustion. Post-burning soil conditions, once again, that microbial activity, and it enhances microbial activity, which leads to the words that I said we'd say over and over again: nitrification, denitrification. We don't need to understand the great details of that because that's not what influences automobiles and everything. And then one of the other main contributors is sewage treatment. Now we're starting to get more into the man-made stuff. Everything that we had done before, talking about fires, natural, talking about, agriculture and raising cattle, somewhat natural. You get to the industrial part, that's where we're starting to produce more greenhouse gases, more N2O. Once again, this is more, we're getting more into the industry now, and with waste management and sewage treatment. So once again, though, even with waste management, something that man is creating and man is putting together, is once again creating nitrification, denitrification. And the only difference you would see is the factors influencing that N2O production. Oxygen levels make a huge difference. How much carbon availability, what kind of carbon elements are in there, in the excretion, in the solids that are coming through, and operational conditions, which is a man-made thing that we try to improve. I actually have a friend that works at the Tonawanda waste treatment plant, and I was able to go and tour it. It's a fascinating subject, and how they work through all this and try to reduce denitrification, reduce nitrification, but at the same time, when they need to increase them in order to get other type of products that they need to get out of it. So another main contributor after waste management, we get to, natural sources. This right here, depending on what document you're looking at, could be the greatest source of N2O creation. So once again, though, comes back to nitrification and denitrification. Once again, even when it comes to the soils, even when it comes to the oceans, you're looking at nitrification and denitrification. This time, the factors influencing are soil, moisture, temperature, organic matter. And if we get into the actual oceans, there's a huge amount of there's a huge amount of influencing that can happen here. You see specifically here, you've got the oxygen minimum zones. I didn't know what those were until I had just took a quick look at this. And the Arabian Sea, just the Arabian Sea, contains 21% of all the oxygen minimum zones. So that's producing and allowing microbes to build such that N2O is produced and released into the air in a much greater capacity, 21%, as compared to all the rest of the ocean. There's upwelling where things are way down deep in the water. It bubbles up through, produces N2O, and you see once again, temperature, nutrient availability makes all the difference again. Now here's where it becomes more relevant to us and what we're talking about. We'll still go through it quickly because it's just a lot of information. It's like drinking from a fire hose. But I think it's important for us to understand everything that goes into it and the contribution, the large or small contribution that fossil fuel burning makes to it. So this right here, we're talking about specifically chemical manufacturing. So we got nitric acid is one of the main, when it's being produced and utilized, it's one of the main producers of N2O. It's in fertilizer production, explosives like nitroglycerin and TNT, all kinds of chemical manufacturing, metal processing, anything that you would use to etch or clean metals, and in woodworking. So all these things make a difference in how much N2O is produced. And you see, I even broke that down, fertilizer production. Once again, even though this is chemical manufacturing, it goes back to fertilizer production in here. There's a large percentage that happens with that. Now, also we have adipic acid. So this is interesting to look at. It's in nylon production, polyurethane production, plasticizers, and that's right, adipic acid in your food additives. Now, I'm not sure if that's the creation of food additives or actually what's put into our food, but it's still something to know that the same thing that they're making nylon with or lubricants with, they're also making your food additives with. Now, this is where we really get into the crux of the fossil fuel combustion. Once again, I'll kind of going through it quickly. We're already, like 28 minutes in. I'm trying to get this done within, I'll try to be done in like 35 minutes or so another 5 to 10 minutes so that I can open up to questions and comments. I want to know what you guys think about this, anything that I'm maybe getting inaccurate or that you've seen in other places. So when it comes to a review of nitrous oxide from emissions in motor vehicles, I wanted to read this one specifically out. The total global warming potential of a motor vehicle exhaust is dominated by CO2 emissions. And I think we all know that. Once again, everything's, based off those CO2 emissions. It's the largest thing going out. And we'll actually see a graphic here in just a second. With N2O contributing only 1 to 2%, and that's actually a pretty high estimate at 1 to 2%. It's actually, most things that I've seen, it's less than 1%. Furthermore, the total mass of N2O emissions from mobile sources is declining. We're improving as we develop different catalysts, as we develop different catalytic converters, we get more efficient with our engines, and we turn over that light duty fleet. The old vehicles are now turning into new vehicles. So the N2O emissions from motor vehicles don't represent a significant contribution to global GHGs. And once again, you'll see that as we get in. I get that from our reference paper right here, SAE. And once again, you would say, they would probably want to favor more saying, hey, it doesn't contribute. But I think it's, even with the 1 or 2%, I think it actually gives a high estimate. So we have different ways that N2O is produced. One of those ways is a high temperature combustion process. And there's different ways that it's broken down of why N2O is produced. Maybe it's from thermal decomposition of the nitrogen compounds. So that's at high temperatures, the nitrogen containing compounds in the fuel. They can kind of decompose and they reacted with the oxygen to form N2O, or maybe incomplete combustion. This is something that we see so often that racers talk about, that a lot of truckers talk about. If they're having incomplete combustion, they see not only their fuel efficiency to go down, but it also creates a higher opportunity for N2O to be created. Fuel composition makes a huge difference. Once again, it's a matter of how things are composed and how they're heated, and the oxygenation of nitrogen in the air. So the nitrogen present in the combustion, it can react with the oxygen at higher temperatures. Once again, we're talking about how temperatures, it's got to be really put into a specific box what temperatures can be utilized, and we'll talk about that in just a second. And then catalytic reactions. So with some combustion systems, the catalysts are used to reduce emissions. And we see catalysts, catalytic converters are constantly used to reduce emissions. And we'll talk about how the oxygen sensor makes a difference in that. So NOx reduction by catalytic converters, you've got ways that N2O can be produced is through ammonia slip, which is probably one of the main things that we need to measure these days is ammonia. If we're looking specifically at N2O, because N2O is very difficult to measure on a real driving emissions. So we measure ammonia because that's what reacts with the oxygen to create N2O. The catalyst composition and temperature makes a difference. Once again, we're talking about composition. Incomplete reduction reactions, secondary reaction. Now, as we continue to go through, we talk about catalytic converters, why they were made. I mean, these things were created back in the 1950s, and they're continued to be improved upon today, but they weren't even required in vehicles until the 1970s, and not even in Europe required on vehicles with the Euro 1 emission standards, not until January 1st, 1993. But they make a huge difference because when you use those catalysts, you're taking things such as nitrous oxides and carbon monoxide and hydrocarbons, and you're transforming like the NOx. You're trying to transform that into nitrogen, which is the most abundant thing. We want to transform that NOx into nitrogen and the carbon monoxide into carbon dioxide, which seems counterintuitive, but it's not. We'd much rather have a whole lot of carbon dioxide in the atmosphere than carbon monoxide, and also taking those hydrocarbons and changing those, separating the carbon out to go into carbon dioxide, and ultimately producing water with the hydrogen that's left over. There's a bunch of different things that we can look at with the catalytic converters. What causes it to react more appropriately? So it's, that's a honeycomb structure in there, so it gets a more effective catalyzation. The type of substrate that's used, there's so many different types. Some of them I'll point out, the platinum, palladium, and rhodium. Those are the ones that use the most. Oxygen sensors become very important to find out how rich the fuel is or how lean the fuel is. Two-way catalysts, which only approach two of the chemicals or two of the emissions, and three-way catalysts which then have something to be able to take care of three of the different types of emissions. So one takes CO and CO2, and another one takes hydrocarbon and NOx and CO. So it's just, there's different, there's two-way catalysts, three-way catalysts, there's different ones that you can utilize. Once again, it comes at selective non-catalytic reduction. This is a little bit different. So this doesn't use a catalyst, but it injects urea or injects ammonia into a flue. And this is more in industrial use. So this is your big flue gases, big industrial furnaces. And this, the temperature range chemical reactions make a huge difference in how this is done as you're injecting that urea. With the temperature range, you're talking about 150 degrees Celsius to 1050 degrees Celsius in order to get the reactions and the reductions that you need in emissions. But at the same time, those high heats allow for N2O to be produced. As we continue to look through, what's the difference between a catalytic converter or a catalyst and SNCR? Usually it's referring to for a vehicle, CO, hydrocarbons, and NOx emissions are the ones being addressed. Whereas in industrial, it's just the NOx emissions that are usually being attacked or trying to be reduced. Of course, the obvious difference is a catalyst versus no catalyst. It's just NH3 injection or urea injection. A huge difference. This is the temperature of your emissions as you're coming out of a vehicle, 82 to 105 degrees Celsius if you've got a gasoline engine or possibly a diesel engine, as opposed to from flue gases, 850 to 1050, as I'd already talked about, degrees Celsius. And these are gas and diesel engines. This is mostly, industrial flue gas operations when you're using an SCR. So this is the catalyst over here, and this is SNCR. So as we get in the next way that we try to reduce emissions, but it can produce N2O, is through selective catalytic reduction, SCRs. Now, most of that can be talked about on being in industrial processes, and that's where it's usually used, but it's also used on large diesel engines and on many, 18-wheelers. And once again, this is where you reduce nitrous oxide emissions by injecting urea. And then it goes through a catalyst where the reaction is more potent and it facilitates the chemical reaction to convert NOx into nitrogen and water. Once again, that's what we're trying to do. We're trying to take that NOx and convert it into nitrogen and water. And you might be familiar with those with DEFs, diesel fluid. So what are the difference between all of them? Just real quickly. Once again, we already compared these two, where with the NOx for industrial and diesel, when we're looking specifically at SCRs, it's got a catalyst and a reductant. And it's varied in its temperature, and it can be used in industrial and diesel engines. So, but once again, these both go after NOx, whereas usually the catalytic converter is trying to approach and eliminate CO, hydrocarbons, and NOx. This gives you overall visualization of how much, when it comes to, I wrote it here, it's an internal combustion engine vehicle, but this is all internal combustion engine, flue gas being produced, which are all internal combustion engines, but I think most of the time people think of those just being in automobiles. But this is everything that's produced in typical emissions, which is why you see, once again, 83% of it is CO2, which is what makes it so important. Now, when it comes to N2O, I'll go to the next slide so you can see. N2O is just a small sliver. Everything I'm reading, it's a little less than 1%. This is what we're trying to approach and what we're trying to eliminate and trying to bring down in vehicles. And it can be hard to measure. It's a very difficult thing to measure in this smaller capacity, when you've only got 1%. And to get it in a mobile, a true mobile sense, it's more difficult to do. That's why we talk about measuring NH3, because that's one of the main things that reacts. And you'll see that most in diesel engines, not so much in gasoline engines. But as temperatures change, as they make changes to engines, you'll see that more and more. And in fact, it was just yesterday I was looking at Toyota has created a vehicle that can burn internal combustion engine that burns solely ammonia. Of course, there's a whole lot of challenges in that, but it's interesting that we're continuing to use the internal combustion engine to try to propel ourselves into the future. This right here is the original breakdown. You saw that in the graphs that I showed before. I won't belabor those right now. And the difference, of course, between these two, you see the difference in the numbers. 5% for natural resource, and that was from an EPA study from 1990 to 99, which is the same study I talked about at the beginning. And then with these, you can see it comes from Our World and Data, and also it comes from Frontiers and EPA. So this is all the information added together. And you can see that natural sources are a little bit higher here. If you have any questions about where I got this information, I'd be happy to share it with you. We can go into teragrams of how much nitrogen or how much N2O was created. I appreciate you guys taking the time. I want to open it up to questions now. If you have any questions, I'd love to hear them. All right. Well, that's a good question. Okay, so we've talked about this, but what is the actual, what are the actual tools that we can use? What are the actual tools that we can use to, measure this? There's a bunch of different ways. There's infrared spectroscopy, electrochemical sensors, photoacoustic spectroscopy. Believe me, I'm reading them off here because if I didn't read them off, I'd pronounce them incorrectly. Photoacoustic spectroscopy, gas chromatography, and Fourier transform infrared spectroscopy. There's all different ways that we can use them. But to your point, what are the things that, would be more accurate? Well, the most accurate ones are like infrared spectroscopy and photoacoustic spectroscopy, because those are more direct measurements. And they actually, like with infrared spectroscopy, there's actually a direct measurement in the absorption of the infrared light by the N2O molecule. So if it sees it, it absorbs it, gives you a direct measurement of it. Photoacoustic is similar, but this is sound waves, and it's looking for specifically for that, it absorbs the light and undergoes some kind of thermal expansion that creates some kind of acoustic sound that is measured, vibration that's measured. I don't completely understand how it's done. I know we've seen them before, we've worked with them before, but understanding how those done, it's not quite as, I'm not real well versed in that. Does that answer your question? I was prepared for that. I was prepared for that question right there. So and once again, I kind of harken back to the things that we're talking about here in Buffalo right now. And hopefully I've got another video that'll actually work for it. You want to know about cross sensitivity and why it makes a difference. Just 1 second. Let me see if I can get this. I'm going to stop this for a second. So cross sensitivity, I've got a great example for cross sensitivity here. Let me make this here. All right. For those of you who like football, here you go. I'm going to talk about cross sensitivity. All right. So hopefully you'll be able to hear this. Hopefully it'll work just as well. So right here, we consider this line right here. This is our NDIR. Let's use it as an NDIR. So if we were using an NDIR to measure something. So we're looking for N2O. So N2O is represented by that football. That's what we're looking for. That's what we're trying to find. But here's what happens. You've got all these other chemicals that are in the way. And as we go through cross sensitivity, it'll see other things. So let's say like this is carbon dioxide and this is carbon monoxide. And we've got whatever, particulate matter, anything that might be flowing through that gets in the way.
Let's take a look at my very scientific replays, okay?
So here's N2O.
As you see, we've got Alan hugging the ball. Everyone I saw saying it was on his right side, but it's more on his left side, and it's dead center. He's just bear hugging.
There's our N2O, and oh no!
The Chiefs player gets in the way of our view.
So the Chiefs player, or the CO2, or whatever other gas it might be, molecule gets in its way. So this is cross sensitivity. We can't exactly see.
Don't worry. I edited with science. I made the Chiefs player invisible to give us some insight into where that ball actually is. There you go.
There you go. There
That's
it is.
where the ball is. He's hugging it.
So what that is, I'll ingest, but now we can see the NO2 molecule, which is what we're talking about with cross sensitivity. So with infrared spectroscopy, photoacoustic spectroscopy, it kind of takes everything out. It makes number 95, it makes that carbon, it makes it invisible so that we don't actually see it. I hope that's a good answer to the question. Hope that worked for you. Yeah, it's a sensitive subject. Does anyone else have any other questions? Could someone just type their hand so I make sure? I want to make sure everybody's, I'm actually able to, see everybody. Just let me know if the chat still works. Yep, okay. Because I got some of the questions and I, was able to look at them, but I wanted to make sure if anybody else has got any questions. Now, one of the things that I wanted to tell you, once again, at Global MRV, we're one of the leading providers of portable emission measurement systems. And we have data capture and analysis solutions that we have found have been very effective with many OEMs and fleets to be able to build a good amount of data, not just a few minutes of data like you'd get in a dynamometer or a chassis dyno. We're able to build hours and hours where we've built 5,000 hours of data just for one OEM alone, just 5,000 hours so they can review their engine development and their emission reduction technologies. Now, this is using our equipment. You can build that amount of information in a short amount of time. And so once again, we're based in Cheektowaga, New York. We serve businesses, original equipment manufacturers, and research facilities in the transportation, automotive, and engineering sectors. We've been doing this since 1999. We've got the skills, we've got the team that can help you. So what I wanted to let you guys know as I'm closing out this webinar, if you refer to this webinar when you call for a service, call for a PEMS device, call for data analysis, any service that we provide, you get 10% off for mentioning this specific webinar. I would like to know who's listening, who it is that finds it interesting, and who is tuned out. So 10% off if you contact us and mention this webinar. Now you can contact us, and I'll share this again just so you can see it. You can contact me directly. I'm always looking forward to talk to people. You can look at globalmrv.com. My email address is earl.leatherland@globalmrv.com. And I'll put that in the chat as well so that you guys can see it and copy and paste it. I'll put it in right now. Here is our website. And I appreciate all the time that you guys have taken for sticking with it the whole way through. I know it was a lot. It was like drinking with a fire hose. But I'd like to talk to you specifically about when it comes to emissions, when it comes to how vehicles are operating, how we can reduce emissions, how we can help, in the entire globe when it comes to climate change. We can give you the tools that you need, or maybe you just need the tools to be able to, justify something that you're doing with the government, because it's not when they're going to come and ask about your emissions reductions. It's not if, it's when. They are definitely going to come and ask, and we'd like to be able to partner with you and help you out. So please contact me at any time. I'm looking forward to talking to you about this information. I hope you have a great day. Here it's about 15 degrees. Well, no, I think today is about 25 degrees, so it's actually gotten warmer. Hope things are going well in your neck of the woods. Thank you for taking the time. Global MRV out.